Hi everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some interesting developments in AI. We'll be looking at a paper titled BitNet.cpp, Efficient Edge Inference for Ternary LLMs. This work addresses the need for efficient ways to run these newer low-bit large language models, specifically ternary ones, like BitNet B1.58, on edge devices, like phones or laptops. The researchers introduce BitNet.cpp, a system designed to speed up inference using less than 2 bits per weight. They've developed a couple of core techniques, a ternary lookup table and int2 with a scale, to make this happen efficiently and without losing accuracy. They're reporting some pretty significant speedups, up to about 6 times faster than standard models. Okay, so speaking of those speedups, let's take a look at Figure 1 here. This bar chart compares the end-to-end inference speeds for a really large 100 billion parameter ternary LLM. We're seeing results on 2 different CPUs, an Intel i7 in blue and an Apple M2 Ultra in pink. You can see different methods along the bottom like llama.cpptmac and finally bitnet.cpptl20, which uses only 1.67 bits per weight. The height shows tokens per second, and while bitnet.cpp clearly stands out, especially on the Apple chip, achieving over 7 tokens per second, significantly faster than the others. Okay, so we saw the speed benefits in Figure 1, but what about quality? Speed isn't everything if the model output changes drastically, right? Well, Figure 2 here addresses that directly, showing an example of text generation to demonstrate the lossless inference capabilities of bitnet.cpp. You can see the prompt at the top, and then the output from the standard float16 model. Notice how the output from bitnet.cpp's lossless methods I2 south, TL1_1, and TL2_1 is exactly the same, identical to the float16 output shown in green. Compare that to the TQ methods at the bottom, where the generated text differs, highlighted in yellow. This visually confirms that specific bitnet.cpp techniques like I2 south and the TL_1 versions achieve their speedup without sacrificing the original model's output quality. Okay, so we've seen the speed and the lossless quality, but how does bitnet.cpp actually achieve this under the hood? Well, Figure 4 gives us a simplified look at the core computation, that mixed precision matrix multiplication we mentioned. It compares 3 ways to do it. There's the standard multiply and add approach, then a bitwise lookup table method. But the key one here is the third panel, the element-wise lookup table. This is the approach bitnet.cpp uses for its TL methods, enabling that efficient handling of the ternary weights we saw earlier. Right, so we saw how the element-wise lookup works in Figure 4. Now Figure 7 expands on the speed results we saw back in Figure 1. Instead of just the one large model, this figure shows performance across a whole range of model sizes, from 700 million parameters right up to 100 billion. Again, it's split by Intel and Apple CPUs. We're seeing comparisons like the lossless I2 south method against float16 and the efficient TL20 method against TMAC and TQ10. The key takeaway is that the speed advantage for bitnet.cpp holds pretty consistently across these different model scales. Okay, so we've seen the speed improvements hold up across different sizes, but what about the quality side of things? Well, these numbers here really quantify that for us. We're looking at end-to-end inference quality using standard benchmarks like Wikitext2, Winograd, and Hellaswag. Notice how the float16 baseline scores are exactly matched by the lossless bitnet.cpp methods, I2 south TL1_1 and TL2_1. Even the slightly lossy TL0 methods show basically identical performance on these tasks. So this confirms we really are getting that speed without sacrificing the model's output quality. So yeah, it really seems bitnet.cpp delivers on its promise. Fast, efficient inference for these ternary LLMs right on standard CPUs without losing that crucial output quality. This is really significant because it pushes powerful AI capabilities closer to edge devices, away from just massive server farms. Well, that's all the time we have for today. Thanks so much for tuning in to the AI Research Roundup. I'm your host, Alex.